In 1860, America was a country on the edge of civil war. Tensions over the abolishment of the slave trade were hitting a boiling point, and the result of that year's presidential election would be decisive in whether or not war would break out. When the votes were counted, Abraham Lincoln was declared the new president, triggering a sequence of reactions that led to the beginning of the Civil War. But here's the thing, half the country didn't know yet when Lincoln was voted in. On November 7, 1860, a rider left Fort Kearny, Nebraska with the news. He was a rider for the famed Pony Express, then the fastest mail service in the country, and its customers paid a premium for its speed. 7 days later, after numerous rider and horse changes and enduring snow and perilous mountain crossings, a rider arrived in California with the momentous news. Now, to us today, waiting a week for news from within the same country seems glacially slow, but 7 days was a record-breaking time. 4 years earlier in the previous presidential election, it had taken months before the Western Coast heard the results. While the achievements of the Pony Express riders are to be admired, our process for communication over distance was butting up against the limits of physical speed and endurance. Something had to change, and that change was already well underway. Within a year, the superhuman feats of the Pony Express would suddenly seem quite unnecessary. Our process of communication would be fundamentally and forever changed by the discoveries of another ongoing process in the field of electricity. 60 years before the Pony Express was galloping across the American continent, in Italy a man named Alessandro Volta invented the voltaic cell, what we would now commonly refer to as the battery. Now, why did this matter? Well, this could provide a steady, continuous source of electricity for experimentation. We have to remember this was well before electricity was commonly available. This was the very early days of scientists just beginning to figure it out. Your average person had no access to electricity and no knowledge of it. Until then, electricity could only be generated via electrostatic charge, that basically being a slightly more refined process of what happens when you rub a balloon on your hair and it sticks up. And it may be that describing how that balloon process works could be a good starting point for everything that's to come. So let's start simple. Every object is made up of something we call atoms. And inside atoms are protons, electrons, and neutrons. Now these all have electrical charge. The protons have a positive charge, the electrons have a negative charge, and the neutrons, as you may have guessed from the name, are neutral. So because of this, every object has an electric charge. But most of the time, that charge is balanced by an equal amount of positive and negative charge, leaving it in a neutral state. Now what happens when two objects rub together, such as a balloon in your head, is that some electrons from one object become stuck to the other, and this creates an imbalance in the charge. One object now has an excess of protons, or a positive charge, and one an excess of electrons, a negative charge. What we've discovered is that opposite charges attract each other, and matching charges repel each other. So when you rub the balloon on your hair gains an excess of electrons, and your now negatively charged hair is drawn to the positive charge of the balloon. And those times when you take the balloon away entirely and your hair is still standing up, that's because each strand of your hair is now negatively charged, and because their charges match, they are all pushing away from each other. So the next step that's useful to understand is what happens when you zap yourself reaching for a doorknob on a dry day. So say you're wearing rubber-soled shoes and walking on carpet. As your soles rub against the carpet, your shoes begin to gather electrons from the carpet, and you slowly begin to move from a neutral charge to an overall negative charge. And as that charge builds, so builds the overall attractive force between those electrons and any positive charge nearby. This also builds the repulsive force between all these electrons getting jammed together and all pushing away from each other. So this means that when you reach out to touch the neutrally charged doorknob, before your hand even touches it, the buildup of force from the electrons looking to get away from each other causes those eager electrons to leap across the gap. And that leap is what causes the tiny spark you can sometimes see. But why doesn't this happen on a wet or a humid day? Well, the world is made up of conductive materials and insulating materials. Conductive materials allow the free passage of electrons throughout, and insulators do not. An insulator says to those electrons,
"You shall not pass!"
One great conductor is water. So on a day when there is moisture in the air, electrons are freely traveling all day long all over the place. So your body never really gets the chance to build up an overall negative or positive charge because of a constant interchange of electrons. But on a dry day, those electrons have a far more difficult time traveling and require much closer distances to be able to travel. So through your various interactions, you can begin to build up a charge, and when you reach for a great conductor like a metal doorknob or the tip of your friend's ear, then those electrons are ready to go. So what does this have to do with Alessandro Volta in Italy in 1800? Well, with inventing the voltaic cell, he was able to generate a constant electric charge through a chemical reaction between a column of alternating zinc and copper plates, each separated by cloth or cardboard soaked in a brine solution. To put it simply, the copper would react with the brine in such a way that it would let go of some of its electrons. That would then transfer to the zinc, that when incorporated as part of a complete circuit would create a flow of charge with a positive terminal at the top and a negative at the base. So while the chemical reaction continues, you get a continuous flow until the chemical reaction stops. Like the small gap between your finger and the doorknob, any conductor you join between the positive and negatively charged points will receive a flow of electricity. Have you ever stuck your tongue on a battery and got a zap? Now you know why. You turned your face into an electron bridge. Volta was able to use the power of process to harness the potential of what was happening at even an atomic level. Now what does zapping your tongue and rubbing balloons so your hair sticks up have to do with the Pony Express and the future of human communication? Well, you'll have to find out next time. There's a lot to this process and we don't want to miss a bit of it. So next episode, we'll find out what we did with these new electrical discoveries and how that continued a process that led us to the telegraph machine that revolutionized the possibilities of our communication.